What is your sphere? Sphere is of two types. Sphere is of two types. Here, this is your first one, and this is your second one. Both of the spheres have charge, positive and charge density, sigma for this one and rho for this one. This is your hollow sphere. It may be conducting and non-conducting. Sometimes it is also known as solid conducting sphere. In this case, it is your solid non-conducting sphere. Note it down, please. These are two types of, okay, these are the spheres, okay, about which we are going to discuss today in two different forms, okay?
Okay, sir.
Yeah, note it down. Have you noted it?
So 1 minute. Answer.
All right. Electric field due to hollow, conducting or non-conducting, you can say, for both conducting or non-conducting. Sometimes it is also called solid conduction.
Solid.
Okay.
Yes, sir.
First of all, we are going to consider a sphere. Of radius r and having charge capital Q. This is your conducting sphere. You can take here. The charge is distributed uniformly throughout the sphere, and your charge is capital Q, having radius r. This is your of radius r. Okay?
Yes, sir.
And now, in this case, we are going to calculate the electric field at 3 different points. The first of the point we can, we are taking here at outside of the sphere. In the second point, we will take at the surface of the sphere. And in the third point, we will take at any point inside this sphere. Are you clear?
Yes, sir.
So we are going to take the first case outside of the sphere. Outside. Okay?
Yes.
For outside, first of all, we should draw the sphere. Okay?
Yes,
First
sir.
of all, we should consider a Gaussian surface of radius r. Consider a Gaussian surface of radius r. This is your sphere of positively charged. And now we can choose a Gaussian, we are going to take a point P outside of this sphere. Suppose that that point is at this position. If that point is at this position, then first of all, we should draw a Gaussian surface, and that Gaussian surface should pass through this point as well. Okay?
Yes, sir.
Then what will be your Gaussian surface? Your Gaussian surface is just like this. This is your of Gaussian surface like this. Okay? And
Yes, sir.
we can take as the radius of this sphere is capital R, and the Gaussian surface is at small r separation. This is your radius of Gaussian surface. Now, can you tell me what will be the direction of the electric field if we take any elementary area at this position? Your electric field always be away from the body, which is in this direction. And for area vector, it is your ds vector. Okay? I mean, the
Yes.
angle between electric field and area vector is 0. Then what will be the flux? We can write here flux through sphere. First of all, we are going to calculate flux. Then we will calculate the electric field. Are you clear?
Yes, sir.
First of all, what is the flux through sphere? Flux through sphere. Your phi is equal to integration of E dot ds. Okay. Phi is equal to integration of E dot ds. In this way, we can mention here phi is equal to E integration of ds and cos of 0 degree. Finally, you get phi is equal to E into S. What is your S? S is your total area of this sphere, which you can
Yes, sir.
take 4 pi r square. This is your r square. Okay.
Yes, sir.
You can consider it equation number 1. Now, using Gauss law. Using Gauss law, your flux is phi is equal to Q enclosed over epsilon naught. Okay.
Yes,
What
sir.
is the value of phi? This is your E into 4 pi r square. You can take Q enclosed as Q over epsilon naught. Okay.
Yes,
Which
sir.
is E is equal to Q over 4 pi epsilon naught r square. This is your value of electric field due to this charged sphere at this point P. Okay. In terms of charge. But in terms of density, you can also mention here, we have sigma is equal to Q over S, or Q is equal to sigma into S, which is your sigma. S, what is your area? Area of this sphere, which is your 4 pi capital R square Q. Now, this is your equation number 4. Put value of 4 in 3. You get E is equal to sigma 4 pi r square over 4 pi epsilon naught small r square. 4 pi is cancelled with 4 pi, and you get E is equal to sigma capital R square over epsilon naught small r square. Note it down, please.
Yes, sir.
Till here, I hope you are understanding.
Yes, sir.
Okay. Is
Yes,
there
sir.
any issue in this part?
No, sir.
Okay, good.
Done, sir.
Okay. Now, in the second part, we are going to calculate the field at the surface. Okay.
Yes, sir.
at surface. We are taking here this sphere which is positively charged. Are you clear?
Yes, sir.
And now if it is positively charged, then you can say that what will be the Gaussian surface drawn for the surface? We are taking any point P at the surface of this sphere. Then what will be the Gaussian surface? I think that Gaussian surface can be drawn just like this. It touches
Yes, sir.
the surface of the sphere. Are you clear or not?
Yes, sir.
1 second. Okay. This
Yes,
is
sir.
your Gaussian surface. You can consider it. Now, if your Gaussian surface is touching the surface of this sphere, then we can say the radius of the Gaussian surface and the sphere is same. I mean, this is your radius of the sphere and this is your radius of the Gaussian surface, which is your small r. Okay. For this case also, your electric field for this particular area, I mean, for this particular small area, your electric field is away from the body, and this is your area vector, n cap you can take also. Okay.
Yes, sir.
For this, we are consider here, sorry, we can consider here small r is equal to the capital R. Then, first of all, we should calculate the flux, then we will calculate the electric field. What is your flux here? Flux
phi is equal to phi.
Your phi is
E
equal
dash
to
E vector
integration of E dot ds cos,
ds cos theta. Yes.
where phi is equal to E integration of ds cos of 0 degree. Or sometime it is also can be written as E into S. Integration of ds will be S. And finally, your area is 4 pi r square. Are you understand it or not?
Yes, sir. Yes, sir.
This is your equation number 1. If for this part, we have already taken here r is equal to capital R. Are you clear?
Yes, sir.
Now, using Gauss law, we can write your flux is equal to total charge enclosed over epsilon naught. Or we can also write Q enclosed is equal to phi epsilon naught. Sorry. Just 1 second. No need to write here. Okay. This is your equation number 2. Put value of 1 into your phi will be E into 4 pi r square is equal to Q enclosed can be considered as Q over epsilon naught. Okay. Where
Yes,
E
sir.
is equal to Q over 4 pi epsilon naught r square. This is the value of electric field in terms of charge Q. But in terms of surface charge density, you can consider that your surface charge density is, as we know, as sigma is equal to Q over A, or S you can see also. So Q is equal to sigma into S, which is sigma into 4 pi r square. This is your equation number 2, and this one is your equation number 3. Now, put value of 3 in 2. You get here E is equal to sigma 4 pi capital R square over 4 pi capital R square epsilon naught. 4 pi r square will cancel from 4 pi r square. Finally, you get E is equal to sigma over epsilon naught. This is the value of electric field in terms of charge density sigma. Note it down, please.
Yes, sir. Done, sir.
Okay. This is the value of electric field at the surface of the sphere. And now, the next one is inside the sphere. Okay.
Yes,
You
sir.
can also write on the inside. For inside, first of all, again, we are going to draw the Gaussian surface. Your sphere first. This is your sphere, and having radius is R, capital. And we know that this is our conducting sphere, and we are choosing any point P inside this sphere. When we draw a Gaussian surface with respect to this point, then we get this Gaussian surface, and the amount of charge distributed upon the sphere is capital Q. Okay, using
Yes,
Gauss
sir.
law, we have already know value of phi is equal to Q enclosed over epsilon naught. But remember that in this case, there is no any charge is present inside this conducting body. So we can write your Q enclosed is equal to 0. Finally, we can say phi is equal to 0. If your flux is 0, then we can also say your electric field inside is 0, or
Yes, sir.
sometime you can also write E at center is 0. Okay?
0.
Yeah.
Yes, sir.
Note it down, please.
Done, sir.
Okay, good. And now we have calculated total 3 values, in which the first one is your E at center. We got 0.
0.
E inside is 0.
0.
E at the surface, sigma over epsilon naught. And E outside, sigma r square over epsilon naught r square. Now, can you tell me that it is clear from all of these 4 values of electric field, there is no any field is here. Sorry, there is no any electric field from center to the radius. From center to radius r of the sphere. Are you clear or not?
Yes,
I
sir.
mean, we can draw it like this. This is your sphere, and if this is your sphere, then we can write here. First of all, this is your we know that this is your center. At the center, there is electric field, which is 0. And from this center to this point, I mean up to the radius r, your electric field is totally 0. Are you clear or not?
Yes, sir.
This is your radius r. Up to the radius r, there is no any electric field. But I mean, this point and this point is clear, I hope.
Yes, sir.
For this point, E at the surface is sigma over epsilon naught. You can look in this equation, it is independent on R. I mean, it doesn't depend upon the position here. Okay. Why?
Yes, sir.
Because we have taken here at the surface of the body. So we can say E surface can be drawn just like as a perpendicular, which is independent to R. You can draw it like this. Okay. Here, E at center is 0. 1 second. Here, your radius is 0, R is 0. And at this position, your R is capital R. For the condition of the E surface, we have taken E small r is equal to capital R. Do you remember it or not?
Yes, sir.
But for the last case, you can look at here. E outside can be written as E is inversely proportional to small r square. And now, if it is inversely proportional to small r square, then we know that what will be the graph for this equation. This graph will be hyperbola. So if you draw for this one, you can draw it like this. This graph is like a hyperbola. Are you clear?
Yes,
This is
sir.
your R, this is your E. Okay. Note it down, please. This is your graph of all of these values of electric field. Note it down.
Okay, sir. Yes.
This represents E is inversely proportional to 1 over R square.
1 by R square.
1 second, which is your E out. E out inversely proportional to 1 over R square. And this is your sigma over epsilon naught. Okay. E
Yes,
at
sir.
the surface. This represents outside. This represents surface. And this one represents inside.
Yes, sir.
Note it down, please. First.
Yes, sir.
Have you noted it?
Sir, 1 minute.
Okay.
Done, sir.
Okay, good. This setting is over. And now we are going to start next setting.
Sir, how many topics are left in this chapter?
After this one, we will solve a single question and this topic will over. Okay. From the next class, we will start chapter 2, electric potential and capacitance.
Electric potential.
Yeah.
Sir.
Electric field due to solid non-conducting sphere. One second, please. Electric field due to solid non-conducting sphere. Okay.
Yes,
this is the next heading.
Okay, sir.
Yeah. Once again, we are going to take an sphere which is uniformly charge distributed of capital Q. So please note it down. Consider a sphere having charge Q. Of charge Q is uniformly distributed. 1 second. This is your sphere. This sphere is of radius R. Charge Q is uniformly distributed charge Q is uniformly distributed through volume of sphere of radius R. Okay.
Yes, sir.
Once again, we are going to do the same work. In this, first of all, we will calculate the field at outside, then at the surface, and in the third part, we will calculate inside. Are you understand?
Yes, sir.
Okay. The first one is outside. First one is outside. For this outside, we are taking again the sphere of this. This is your sphere of charge plus having positive charge here, capital Q. And we are going to calculate the field at this point. If this is a point here, this is your Gaussian surface, which I am drawing here. This Gaussian surface is of radius small r, and the sphere having radius capital R. What is the direction of electric field? Once again, it is away
Outside.
from the
Yeah.
charge, and unit vector is along this direction. Okay. I hope
Yes, sir.
everything is same for this also. Okay.
Yes, sir.
What is your flux? Flux through sphere. Phi is equal to integration of E dot ds, or it can be also written as E dot ds cos theta. You can write here. You can write here E dot ds cos of 0. Finally, you get phi is equal to E into 4 pi r square. This is your equation number 1.
1.
And now we are going to use the Gauss law. When you use by using Gauss law, phi is equal to Q enclosed over epsilon naught. What is your value of phi? Your value of phi is, 1 second, put 1 in 2. This is your 2. When you put it, E into 4 pi r square is equal to Q enclosed can be taken as Q over epsilon naught, and E is equal to Q over 4 pi epsilon naught r square. We have also sigma is equal to Q over A or S, you can say. This is your solid sphere, so its volume will be sigma is equal to Q into S. Sorry, its area will be sigma over 4 by 3 pi r. Okay.
Yes, sir.
And put this value in this equation number 3. This is your 4. Put 4 in 3. We get E is equal to sigma 4 by 3 pi r cube over 4 pi epsilon naught r square. 4 pi will cancel from 4 pi. You get E is equal to sigma r cube over 3 epsilon naught small r cube. Note it down, please.
Yes, sir. Done, sir.
All right. And the next one, outside. This is your
Outside
outside.
the,
And now we are going to
on
calculate
the at the surface.
at the surface. Okay. For second one, at the surface. We have already calculated from the last equation. We have already know E at the surface. We can take at the surface, your small r will be equal to the capital R. Am I right?
Yes, sir.
So it will be sigma, rho, small r, what is your last equation? 1 second. Sigma r cube, 1 second. Sigma,
Sigma.
1 second. Rho r cube is equal to rho r cube over 3 epsilon naught small r. Okay, this is the last equation.
Yes, sir.
Okay. But for at the surface,
Sir, it was rho or it was sigma?
this is a rho. This is a sigma.
No, sir. You wrote sigma right last time. Last equation.
No.
You wrote 7 minutes.
1
Sir,
second.
you wrote sigma, sir.
I have taken sigma.
Yes.
Sorry. Just 1 second. It is your volume charge density actually. Okay. K into V. This is your. Please correct this.
Yes,
Okay.
sir.
This is your volume charge density. Sorry for it. Volume charge density over V. Q is equal to rho into V. V, you can choose here rho and rho. Now it is correct. Okay.
So 1 minute. Done, sir.
Okay. And now we have rho r capital R cube over 3 epsilon naught small r cube at surface. At surface, small r is equal to the capital R.
Yes, sir.
So we can write here E at S is rho r cube rho r cube over 3 epsilon naught r cube. This is your one second. This is the square not cube. Make it correction. Finally, you get ES is equal to rho R over
R.
3.
3 epsilon.
Note it down, please.
Done, sir.
Okay. At
Center.
inside.
Yes.
Inside. What will be the value inside of this sphere? Again, we are going to draw the sphere again. This is your sphere. And the amount of charge is distributed uniformly on the surface. Okay.
Yes, sir.
We are going to take any point. 1 second. What is the radius here?
Sir,
Radius capital R. Okay.
Capital R.
We are going to take any point inside this sphere like this. We are choosing this point. And we have already know this is a non-conducting sphere. So what will be the amount of charge within this Gaussian surface? Okay.
Yes, sir.
And take it as radius small r. Right?
Yes, sir.
So please mention here. Consider a Gaussian surface of radius small r, which is your phi is equal to integration of P dot ds. Cos theta you can take, but there is no need to take the cos theta. Okay?
Yes, sir.
Because we know the unit vector and the field vector both are in the same directions, right? Finally, you get phi is equal to E into 4 pi r square, right? This is your equation.
Yes, sir.
Now, using Gauss law, the phi is equal to charge enclosed over epsilon naught. This is your equation number 2. And can you tell me the amount of charge enclosed? What is your total charge? Your total charge is capital Q. And the amount of charge enclosed within the Gaussian surface is this. This is your Q enclosed. Okay. Can
Yes,
you tell
sir.
me Q enclosed is greater than Q or less than Q?
Q enclosed is less than Q,
Less
right?
than capital Q. Are you clear?
Yes, sir.
So in what amount? Sorry. So what will be the volume of that amount of charge which is Q enclosed? We can
It
write
will
here.
be Q minus.
Enclosed is charge on volume. What is the volume of this Gaussian area?
4 by 3.
Okay, 4 by
4 by
3
3 pi r
pi
square.
r cube.
Oh, cube, yes, sir.
And now, what will be the volume charge density? Your volume charge density is?
Volume.
Just 1 second. 1 second, please. No need to write still now. First of all, right here. Yeah, no issue. Rho is equal to Q enclosed over
by
epsilon
epsilon
naught.
0.
Rho is equal to Q enclosed over volume. So what will be your Q enclosed? Rho into volume, which is Q enclosed is rho 4 by 3 pi r
Square. Cube, yes.
Are you clear till here?
Yes, sir.
Now we can put here this is the equation 1, this one is 2, and this one is 3. Okay, equation number 3.
Yes, sir.
Put 1 and 3 in 2. This is your phi is equal to Q enclosed over epsilon naught. What is the value of phi? E into 4 pi r square. What is your Q enclosed? Rho 4 by 3 pi r cube over epsilon naught. 4 pi is cancelled by 4 pi. E is equal to rho r cube rho r cube 1 second over epsilon naught r square. After calculation, you get rho into R over, sorry, this is 3 also. 3 epsilon naught R square, then it will be 3 epsilon.
3 naught epsilon.
Note it down, please.
Yes, sir. Done, sir.
All right, good.
Sir, just a minute, sir. 1 minute.
Sorry.
Sir, just a minute, sir. Sir, I'm coming in 1 minute, sir.
Okay, okay.
Yes, sir, you can continue.
All right. And now, once again, we are going to write all of the 3 questions which we have calculated till now. We have E outside is rho R cube over 3 epsilon naught R square. The second one, E at the surface is rho R over
cube 3 epsilon.
naught. Okay.
Yes, sir.
And in the last, E inside is rho R over 3 epsilon naught. Are you clear or not?
Yes, sir.
Can you tell me for what will be the graph for this E inside? You can look at here in this equation. Your E is directly proportional to R, so we can say that your graph will be
a straight line, right?
Are you clear? And
yes,
for this one, you can look at E outside. E is inversely
proportional. It will be a curve, sir.
It will be the hyperbolic graph.
Yes, sir.
And E at the surface doesn't depend on the R.
Yes.
Okay. Are you clear or not?
Yes, sir. So it will be uniform, right?
Yeah.
A straight line.
Yeah. So what will be the, no. It never be a straight line. It is discontinuous.
Okay.
Right? Yeah. It is discontinuous at this point. Okay. At this point, your graph will be discontinuous.
Okay, sir.
So we can draw here. Are you taking mathematics or biology? Sir,
bio, sir.
Bio, not mathematics.
No, I don't have maths.
Okay, no issue. This is your sphere, and
yes, sir.
Up to the radius R, up to the radius capital R, your graph is directly proportional. So we can say that it is like this. Okay.
Yes, sir.
It is like this. R is equal to R. Yeah. But after that, your graph will be hyperbolic. Okay.
Yes, sir.
Note it down, please. At this position, your R is 0. At this position, if you want to understand, this is your position of R is equal to R. This is your R is less than capital R, and this one is R is greater than capital R. This represents is inversely proportional, I mean E outside inversely proportional to R square, and this one represents E inside, which is directly proportional to R. This is your discontinuous point, and this point represents R is equal to R, which is this equation. For this equation,
Done, sir.
right? Now we are taking a question, and we will try to solve this. Show that charge Q given to a thick metal plate distribute equally on both sides. Distribute equally on both sides. Okay.
Yes, sir.
Can you solve it or not?
Sir, 1 minute, sir. I'll just tell you. I'm trying to solve it, sir.
Please try to do it.
Yes, sir.
This is your metallic plate. It is saying that this is amount of charge Q is given, and distribute equally on both sides.
Yes, sir.
Distributed, right? It distributed equally on both
On
sides.
both sides.
Yeah.
So there are 2 charges or 1 charge, sir? Only 1 charge, right?
Only Q amount of charge. Q is, you have already know Q in the sense.
Yes.
It is an amount of charge. I mean packets of charge.
Yes, sir.
Not a single charge here.
Sir, how do you solve this?
Okay. You can take it, first of all, we can consider that the amount of charge on this side is Q1 and this side will
It's
be Q
Q2.
minus Q2.
Q
Sorry,
minus-
Q minus Q1.
Yes, sir.
Are you clear or not?
Yes, sir.
And the density on this side is sigma 1.
Sigma.
And density on this side is sigma 2.
Sigma 1, 2. Okay, yeah, 2.
Okay.
Yes,
What
sir.
is the amount of, what will be the field inside the plate? Okay. For this point, the electric field is along this side.
Yes, sir.
Or this it is along this side. You can make it, you can write it inside the plate, either E1 plus E2 is equal to 0, or you can write E1 minus E2 is equal to 0. Am I right or not? As we have already know, both are opposite in
Yes,
direction.
sir.
So we can take
Because they are in opposite direction. Yes.
Okay. Finally, we can also write E1 is equal to E2. If E1 is equal to E2, we have already know the electric field due to the plane sheet of charge, or you can say for the plate, is sigma over 2 epsilon naught. Do you remember or not? But for Q1,
Yes, sir.
you can write it sigma 1 over 2 epsilon naught. For E2, you can write sigma 2 over 2 epsilon naught. 2 epsilon naught will cancel from 2 epsilon naught from another side. It will be sigma 1 is equal to sigma 2. Sigma 1 can be written as Q1 over area A. And we have already know both of these areas are same. You can write here
Yes, sir.
Q2 over A. A is cancelled with A, and you get
So everything is equal.
Q2. Oh, just sorry. I did a mistake here. What is the amount of charge for sigma 2? It is Q minus
Sir, Q minus Q2.
Q1.
Q1,
Okay.
sorry. Q minus Q1.
Yeah, it will be your Q minus Q1. Finally,
Yes, sir.
you get Q1 is equal to Q minus Q1. Transfer this value from right hand side to left hand side. You get
2Q1
plus Q1 is equal to Q. 2Q1 is equal to Q.
2. Yeah,
Q1
Q.
is equal to Q by 2. If Q1 is equal to Q by 2, then what will be Q minus Q1? You can write it Q minus Q1 is your Q by 2. Once again, Q by 2. Thus, charge is distributed
Equal.
equally on both sides.
Both sides.
Okay.
So we just had to prove like everything is equal.
Yeah. Both sides, your charge will distributed. If your configuration on both sides is same, are you clear? This is the main condition. If the configuration is same, then your charge will be equally.
And sir, if the value was different on Q1 and Q2, it wouldn't be same, right?
Yeah. Okay.
So we can just tell from the figure it's same.
Sorry?
We can just tell from the figure it's same.
No. It is given already that your amount of charge, which is capital Q only. Okay.
Yes, sir.
Or another cases, it may be possible that your situation may change. Okay.
Yes,
it
sir.
depends on your question.
Yes, sir.
Yeah.
Done, sir.
Okay. Good. And I have another question. If
Yes,
you
sir.
can do it.
Sir, same type.
Yeah, I think nearly same. Suppose that a thick metallic plate sheet is given here.
Yes,
The
sir.
question is calculate a thick metallic plane sheet is given. The positive charge are produced here. Sigma and sigma. This is your region 1. And this one is your region 2. This one is your region 3. It is saying
Yes,
that
sir.
calculate the field in region 1, region 2, and region 3 due to this metallic plane sheet. Sorry, due to this thick metal
Okay,
sheet.
sir.
Okay.
Okay.
Right here. Thick
Yes, sir.
metal sheet. This is your thick metal sheet.
You
Okay.
have to find in region 3.
Yeah.
Okay.
Calculate field, electric field mainly.
Yes,
Field
sir. Okay.
at in region 1, 2, and 3 due to thick metal sheet.
Yes, sir.
Can you solve it or not?
Sir, I'm trying, sir.
Okay, good, good.
Sir, isn't this same as like last class we did, right?
Exactly. We have
Like
already
E
solved.
is equal to E1 plus E2, and then we'll do this.
Yeah, yeah.
First, we take the lines outwards,
Hmm.
and then second one. Region 1, 3. Sir, for region 1, we should do like this, right? E is equal to E1 plus E3.
No, 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 no. E1
So then,
yeah, look at here. In region 1,
yes, sir,
if you draw, due to this surface,
it will be outwards.
okay, you can take it like surface 1, and this is your surface 2. Okay.
Okay, sir.
And now your field line will always be away from the surface, sorry, away from the charge.
Yes, sir, because it's
R1.
positive.
And
Yes.
just similarly, it is also away from the charge due to surface 2,
Yes,
charge
sir.
of surface 2. Are you clear?
Yes, sir.
Similarly, in this region, your situation is same for 1 and 2.
Yes, sir.
Are you clear or not?
Yes, sir.
You can write here E1. It is your
E2.
E1, E2. Now, if you go to solution, then we can write here E for first region is E1 plus of,
Plus E2.
okay.
Yes, sir, that's what we did last time
And
also.
it is
Then
your
sigma by
over
2 pi epsilon
2
0.
epsilon naught. This is a
Yeah.
plane. Okay, it behaves
Yes,
just
sir.
like a plane sheet. And it is
Yes, sir.
also sigma over 2 epsilon naught. Finally, you get 2 sigma over 2 epsilon naught. And hence you get sigma over epsilon naught. 2 is cancelled with 2. Are you understand it or not?
So that's what I did, sir.
This is the solution for first region.
Yes, sir, that's what I did. That's why I was asking you, is that correct?
Okay.
E1 plus E2.
Similarly, for the second region, your condition is same.
Yes.
And what will be the direction? Just 1 second, please.
Yes, sir. Yes.
I'm going to mention the direction also. Okay.
Okay.
Now,
Then
can
it
you
will
tell
be
me?
minus I cap,
Yeah,
right?
yeah. Yeah, exactly. This is your minus of I cap
Yes, sir.
plus sigma over
Sigma.
2 epsilon naught minus
Minus
of.
I cap.
Once again, you got 2 sigma
2 sigma
over 2
2
epsilon naught
pi epsilon 0.
minus of I cap. Are you understand or not?
Yes, sir. Yes, sir. Direction.
Okay. 2 is cancelled with 2. Finally, you get sigma over epsilon naught minus of I cap
Yes, sir.
in vector form.
Yes, sir.
Similarly, for the
That's
second
region
region,
1.
this is your E is equal to E1 plus E2, which is your sigma over
Is equal to sigma
epsilon
by 2 pi epsilon. Sorry, 2 epsilon
minus
0
I cap.
minus I
Sorry,
cap
plus I cap.
plus
Not
sigma by 2 epsilon 0.
this is
Sorry, yeah. X axis plus
plus
positive
I
x.
cap, which is your sigma
Yes.
over 2 epsilon naught I cap. Finally, you get 2 sigma over 2 epsilon naught I cap. 2 is cancelled with 2. Once again, you get sigma over epsilon naught I cap, which is your E of 2. Are you understand or not? Hence, we have calculated for these
Yes, sir.
two.
Yes, sir. I did the same way.
But can you tell me,
Yes, sir. I did.
once again, can you tell me what will be the direction due to surface 1 in region 3? It will be away from the charge
Surface 1. Yes, sir.
due to surface 1.
Yes. And
And
so net force will be 0 for net surface 2 also, it will be away.
it also away from the charge. Okay.
Yes, sir.
You can write here E1 and you can write here E2. Both of the densities are same. We can say that E3 is equal to E1 plus
plus E2.
E2
Yes,
E1
sir.
is your sigma over epsilon naught I cap
Yes, sir.
plus sigma over epsilon naught minus I cap. Finally, you get sigma over epsilon naught I cap minus sigma over epsilon naught I cap. You get 0.
Yes, sir.
In another way, you can also say, both of the surfaces have same amount of charge. I mean, surface 1 and surface 2 having same amount
Same
of
amount
charge.
of charge.
Okay. So the net field will cancel each other.
Yes, sir.
And we can
So
say the
that
net field inside
will cancel each other.
the metal sheet is 0.
Yes, sir.
Okay, you can mention here. Hence, net field
Net field